Hello and welcome to our talk on semantic segmentation with scanning radar. My name is Daniele De Martini. I'm a postdoc assistant at the Oxford Robotics Institute. The primary author of this paper is Kaul, a doctoral student at the FMCW Center of Doctoral Training in Autonomous Intelligent Machines and Systems. The other co-authors of this work are Matthew Gadd and Paul Newman. Today we are going to talk about an efficient way to train a neural network to understand the scene sensed by a scanning radar. Semantic segmentation is a well-studied task in robotics and autonomous systems. Nevertheless, most of the work has been done with cameras and lidars, and little work has been done with radar so far. Radar has notable advantages compared to traditional sensors like lidar and cameras. First, like lidar sensor, it provides a 360-degree view, but it will reach hundreds of meters in range, and every return is a dense return, more like a camera in that sense. But moreover, and probably most importantly, radar is inherently robust to weather conditions. Indeed, it can see through rain, snow, fog, and dust, as it was a clear day. Indeed, for cameras, you usually need to train your model with all kinds of weather conditions: sunny, fog, snow, rain. But those could be either rare or difficult to capture or even difficult to label. So what you normally do is that you train your models using synthetic data that are created from favorable conditions. But all of this is not needed with radar because it is inherently robust to all these conditions. This work is in line with a collaboration between the Oxford Robotics Institute and Navtech Radar to develop both the hardware and the software for all-weather radar navigation. So far, radar seems the perfect sensor, but it has complex measurement returns affected by multipath reflections, speckle noise, and internal noise characteristics. Moreover, like LiDAR sensors, radar senses the environment in a 3D way, but it compresses it into a 2D dense representation. This limits the discrimination between objects with similar appearance. This makes labeling of such sensor quite labor-intensive, even for expert users. This is why in this work we propose an efficient and automatic way for labeling radar scans. We propose to use state-of-the-art semantic segmentation techniques for cameras and LiDAR technologies to automatically label radar scans. For this, we will leverage the recently released Oxford Radar Robocar dataset. We use a pre-trained camera segmentation network to create dense representations of the scene. Since the camera network is going to work good in fair conditions, we are going to label the radar in fair conditions as well. But since the radar is robust to bad weather conditions, it will perform good even in bad weather conditions. Moreover, to emulate the field of view of the radar, we are going to stitch together the 4 cameras that are recording the scene all around the car. LiDAR measurements are used to project the camera labels into a 3D world in the same frame of reference the radar lies in. We then accumulate those labels using an odometry post chain to cover as much as the radar scan as possible up to the sensing range. We do so because the LiDAR sensor has a shorter sensing range than the radar sensor and is going to return sparser and sparser returns at longer ranges. The odometry post chain is taken from our ground truth dataset, which is made by optimizing visual odometry, visual loop closures, GPS and INS, so it's quite trustworthy. Once we have the labels, we can use standard supervised learning techniques to train a neural network which takes as input raw radar scans and as output the labels we produced. We used a neural architecture which is based on DeepLab with few modifications. This work is not about the neural architecture itself, but about the procedure to train the neural network. We are sure that there are network improvements which can be made. From the 30 classes that Cityscapes defines, we decided to limit our network to learn 7 different classes that are listed here. We made the choice because the radar, as we said, limits the discrimination between objects with similar appearance. Here we can see a qualitative example of our work. Here is a raw radar scan in Cartesian representation. From it we can see different objects, from people to walls to cars, but also multipath reflections. Using our pipeline, all the visible objects are labeled, although some inconsistencies are brought in. These are caused by the not perfect calibration of the sensors and the not perfect semantic segmentation network from the camera. Nevertheless, the neural network is able to generalize and remove most of the inconsistencies and the multipath reflections. It is true that not all the inconsistencies are removed, so we know there is room for improvement. Here are the quantitative results of our pipeline. We see that most of the errors arise from non-building class, with the biggest classes like building, vegetation or cars with the highest accuracies. Interesting is the bike class. Indeed, it is mostly misclassified either as a vehicle, probably because of the position in the scene, so in the road, or as a vegetation or a construction class. We inspected the camera streams and we saw that most of the bikes were either laying on a wall or in bike racks. So the first one really resembling constructions and the other one that were quite similar to vegetation. You can find out more about the broader project this work fits into at the IEEE workshop listed in the first reference. You can also read more about the deep lab architecture in the second reference. We would like to thank the funding body that supports this project as well as our partners. Please do not hesitate to contact any of the authors if you have any questions about this work. Thanks for watching our presentation and we hope you will enjoy the rest of your IEEE conference.